So let's start today's class. Yes. Today's class is the second part of the sensation, sensory information and systems. Yes. It's focus on the auditory sensation and the visual sensation. Yes, firstly is in the auditory sensation. Yes, you have the ear here, and also the eardrum is here, and after the eardrum, three small bone is here. 1, 2, 3. These three bone. After receiving the air pressure vibration at the eardrum, this vibration is transmitted via these three chain of three bones. Yes, this is a oscular chain. 通知骨 malleus, incus, and stapes is here. Three bones is here, and after it, this vibration is go and back vibration is here by this final small bone, and then this vibration makes the cochlea. This has looks like this screwing shape. Yes, here this mechanical vibration is translated into the electric signals. Okay. So firstly, I will show this small introduction video process of hearing animation here.
The ear has three parts: the outer ear or auricle, the middle ear, and the inner ear. The auricle, the visible part of the ear, collects sound waves and directs them to the auditory canal. The auditory or ear canal is lined with cilia and ceruminous glands. The earwax from the ceruminous gland and the cilia protect the ear from entry by foreign matter. The thin tympanic membrane separates the outer ear from the middle ear. Sound waves cause it to vibrate. The three tiny bones of the middle ear are the hammer or malleus, anvil or incus, and stapes or stirrup. These bones pick up the vibrations from the tympanic membrane and transmit them to the inner ear. The eustachian tube of the middle ear opens into the pharynx and permits air pressure to equalize between the ear and the outside air. The inner ear is maze-like, consisting of bony and membranous structures surrounded by fluid. Semicircular canals are fluid-filled bony loops that help maintain our body's balance. The cochlea is a fluid-filled, snail-shaped structure that houses the organ of Corti, the true organ of hearing. The fluid aids in the transmission of the vibrations. The organ of Corti changes the vibrations into nerve impulses that are picked up by the auditory nerve. Sound waves are collected by the auricle, or outer ear, and sent to the auditory canal, tympanic membrane, ear bones, and then to the cochlea, where the vibrations are changed by the organ of Corti to nerve impulses and transmitted by the auditory or cochlear nerve to the temporal lobe of the brain for interpretation.
Yes. This eardrum vibration is translated by these ear bones, three ear bones, and cochlea makes the mechanical vibration into the electrical signals. Okay, that is transmitted to the brain. Yes, the cochlea is looks like this. Yes. Yes, three rooms, three chambers here. The middle chamber, the upper chamber, and the lower chamber. And the middle chamber, it has some nerves. Nerves is located on this middle chamber layer. So it is worked as a frequency discrimination because the some vibration is the ear bone vibrate this end tip of this element, and the which part is vibrated most vibrated is depending on its vibration frequency. Okay, vibration frequency. Because when the higher frequency, this part is the most magnitude. And the low frequency, the end of this element is most magnitude. Okay, so this element, this long element, is making the frequency separation. So the which frequency is this bone and this ear received or not is discriminated by this organ. Yes, the mechanism is explained maybe this video.
Many of us take for granted a very extraordinary organ, our ears. To understand the ear, we need to understand what sound is. The speakers you are listening to right now are vibrating, flexing in and out, causing a wave of pressure through the air. The frequency of these waves, or the speed at which the sound creating surface moves back and forth, affects the pitch of the sound. The level of air pressure in each wave is directly related to how loud the sound is. The outer part of our ear catches these waves. It faces forward and has a specially designed structure of curves, helping us to determine the direction of the sound and also emphasize the frequencies used in human speech. Now that the sound waves are caught, they travel through the ear canal and strike against our eardrum, a thin membrane about 10 millimeters wide. Now that we receive the sound, the middle ear transfers this energy. The smallest bones in your body, the malleus, incus, and stapes, start in motion. The malleus is attached to the eardrum, and as the sound travels along, the force is amplified by leverage until it arrives at the stapes, which acts like a reverse piston, creating waves in the fluid of the inner ear. The most significant increase in pressure is caused by pneumatic amplification. The face of the stapes has a surface area of about 3.2 square millimeters, while the eardrum has a surface area of 55 square millimeters. Using this, along with leverage through the malleus and incus, the final pressure is 22 times greater than when the sound first arrived.
Pressure is
now we come to the most complicated part of the hearing, the cochlea. In reality, it is coiled up, but it is easier to understand straightened out. There are actually 3 chambers inside, but let's take a look at the central part. The stapes is causing pressure waves to travel through the structure. Along the inside wall is about 20 to 30,000 reed-like fibers. As the waves move along, they encounter fibers with the correct resonant frequency and energy is released. These fibers aren't actually what give us the signal that we heard something. There is a special structure next to these fibers containing hair cells.
Yes.
When the fibers resonate, they cause the hair cells to move, which then sends an electrical impulse to the cochlear nerve and onto the brain. Certain pitches of sound will resonate in specific locations, and louder sounds will cause more hair cells to move. Our brain interprets all this raw data, making it possible to enjoy things like music or an engaging conversation. Just to think that all of this is happening in your head right now at full speed. This is just one of the amazing systems found in the human body that go far beyond our humble human understanding.
まあいいや。このヘアセル is here. So depending on the frequency, which part of hair cell is yes. Hair cell is some liquid pressure. Receiving some liquid pressure, the hair cell is bended. So the hair cell, this hair is bended. Some electrical signal is produced by this nerve. Okay. Yes. The next is here. This is a model analysis. So this is the ear drum and some 3 bones. Ear bones is 3 ear bones. These 3 ear bones and also this ear drum is modeled finite element method, FEM, you can hear. And the, yes, which part is magnituded, emphasized or not, is we can estimate. Because some patient has lack of some part of the eardrum or some injured by some accident. So to treat and recover this eardrum, so which part, which frequency the patient cannot hear or not is we can estimate by this model analysis. Okay? So the modeling is important to estimate the patient condition and how to recover this injury. Okay? ちょっと frequency analysis of middle ear. I will show this. Yes, small element divided in small element, and yes, this is an eardrum. 3 ear bones here. Looks like this. Only that. Yes, this is more another approach about the mechanical engineering, the model analysis. Yes, this is cochlear's the middle layer, middle chamber layer. This is a 基底膜 base ear membrane とか laminar basilaris とか言って it is called. So this is pressure is here, pressure is given here, and this is yes, material vibration, mechanical vibration, and also the liquid vibration. So the simultaneous equation and also boundary condition and initial condition is pushing here. So therefore the specific frequency can be analyzed. Specific frequency distribution can be analyzed. So for example, the wave input 1 kHz is inputted. The which part is the most excited can be estimated, okay, by mechanical analysis. So to support to auxiliary system or substitution system of the ear, there are several methods. One is an assist device, and the second is a tactile sense, usage of the tactile sense, and the third is a visual sense, usage of the visual sense. So in place of the auditory sense, sometimes in some cases tactile sense is used. In some cases, visual sensation is used. Okay. So the firstly is some support device, middle ear implant, or the next part is a cochlear implant. Firstly, about the middle ear implant. Middle ear implant is a patient who lost the ability of eardrum. So replace the eardrum and the 3 ear bones. This vibration cantilever is replaced to this part. So the hearing the microphone receives the auditory signal, and it will be changed into the mechanical vibration to the cochlea. Okay, this is a middle ear implant. ちょっと見ておりますか?
The vibrant sound bridge is an alternative to conventional hearing aids or bone conduction devices. The vibrant sound bridge middle ear implant system consists of an externally worn audio processor and an implant which is placed surgically under the skin. The audio processor is held in place by magnetic energy and can be worn comfortably under or over the hair. Sounds are picked up by the microphone in the audio processor. The audio processor converts environmental sounds into electrical signals. The electrical signals are transmitted through the skin to the implant. The implant relays the signals down the conductor link to the floating mass transducer, abbreviated FMT. The FMT converts signals into mechanical vibrations, which set the structures of the middle ear into motion. The FMT has a frequency range of up to 8,000 Hz. The versatility of the FMT has led to a variety of surgical applications known as vibroplasty. The incus vibroplasty, for example, involves affixing an FMT to the incus. This procedure is a treatment for sensory neural hearing loss.
Yes, this is for the patient who can maintain keeping this cochlear function. So this part, only this part, this eardrum, and to replace of this eardrum, in place of the function of eardrum and 3 bones, this middle ear support system is used. So this is producing the mechanical vibration here. Okay?
Mechanical vibrations can be controlled to be slower or faster depending on the particular type of hearing loss. The FMT transfers vibrations to the inner ear and onto the brain where these signals are perceived as sound. The success of the vibrant sound bridge as a treatment for hearing problems originating in the middle ear can be traced to its unique design. Use of the FMT is independent of skull growth because the FMT need only be affixed to the structure which it stimulates.
Yes, this is put on the outside of the body, and this part is implanted into the body. Okay, implanted under the skin. So the some energy and signal is transmitted via the skin. Okay.
The audio processor of the Vibrant Sound Bridge offers users the state-of-the-art in hearing technology, including intelligent signal processing, natural sound quality for both speech and music, dual microphones, as well as an improved signal range and a selection of various listening programs. Because the audio processor is an external component, it can be replaced with a newer model as technology improves. This is one of the distinct advantages of the partially implantable system. After a simple fitting, long-time users are able to take advantage of the newest technological improvements years after receiving their first implant.
Yes. Yes, this is an example of the middle ear implant. Okay. Yes, this is also the same as yes. This is the yes. Directly connected to this final ear end. Yes, the second configuration is the cochlear implant. So the patient who cannot work this cochlear also. So in place of this eardrum and ear bone and cochlear, it should be stimulate the nerve cells directly. So the electrical component is necessary. Yes, I will show also the video. Cochlear implant こっちかな。ちょっと短いショートビデオ。Yes, I will show.
In case of sound waves striking the ear, they pass through the canal to the eardrum. From there, the sound waves are mechanically transmitted to the inner ear and amplified. In the inner ear, you can find the cochlea. The cochlea consists of 3 different canals. The middle canal is the organ of hearing and consists of sensitive hair cells. The hair cells can be stimulated electrically and forward the signal to the nerves and then onto the brain. In most cases of deafness, the hearing nerve still remains functional, but the hair cells have been damaged or even lost.
Damaged, yes.
In a cochlear implant system, sound enters a microphone and travels to an external mini-computer called a sound processor. The sound is processed and converted into digital information. This digital information is sent over a transmitter antenna to the surgically implanted part of the system. The implant will turn the sound information into electrical signals that travel down to an electrode array inserted into the tiny inner ear or cochlea. The electrodes directly stimulate the auditory.
Yes, electrode, electrode can, it says, directly stimulates this auditory nerves. Okay? Electrode is inserted into this cochlea. Okay?
Nerve, sending sound information to the brain. Bypassing the damaged inner ear, the cochlear implant provides an entirely new mechanism for hearing.
Yes. For example, the 22 electrode is arranged on this along this cochlear tube, so that 22 kinds of frequency can be provided to this ear organizations. Yes. Yes. This maker, the manufacturer of this kind of cochlear implant is the Australian and American or Australia presently. These three is a big main company to provide these products. Okay. Yes, so it looks like this. This is Advanced Bionics Corporation's Bionic Ear System Harmony. So, for example, yes, I want you to think how much cost this middle ear implant or the cochlear implant. For example, the cost example, it will be divided surgical cost and this product cost and also the hospitality cost, examination, hospitalization, and rehabilitation. How much cost it has? For example, surgical cost, how much? 成田。surgical cost、これ入れるのにどのぐらいかかりますかね？ How much cost?
1000万ぐらいかかるんじゃないですか。
30万。
あれそんなですね。
30万円。これ、yes, this product, how much? Answer. How much?このプロダクト。cochlear implant product. How, for example? 2,000 dollar? 2,000 yen? 2,000 yen? 2,000 円ですか? Yes, this is 2 million, about 3 million yen. Okay? And the hospitalization, maybe 1 week, not only 1 week, but maybe the 100万円ぐらい. Yes, totally, so the 400万円ですね. 4 million yen it costs. But in Japan, it has yes, insurance. Health insurance can be applied only 10 several 万円 or several 万円. Yes, about 100,000 yen. Okay, 100,000 yen means 1 million yen or more or less. Okay. only that we can use it because health insurance can be applied this treatment in Japan. I don't know the Chinese condition. Yes. Another way to provide is tactile, using the tactile sensation. Yes, some microphone can receive the auditory signal, and it is divided by using the filtering and changing into the mechanical vibration. Yes, this pin is vibrated by some, for example, a piezoelectric device can be used to make the vibration. Okay? And also the watching is, for example, the hand language, hand gesture language, or this is a robot. Robot is a balloon robot. Balloon robot is also can do the hand gesture. And about 20 years ago, Stanford University has developed the robotic alphabet, RALPH, for the hearing impaired and visual impaired. Use a tactile display. Yes, touching or something. Yes, I will show a little bit about the robot. Robot, only the balloon robot.
These are all Nabbits, the brainchild of Assistant Professor Takahashi at the Tama University of Arts. Nabbit is a compound of the words balloon and robot, and that's exactly what they are. Robots as soft and airy as balloons. They're made out of nylon film, which is blown up like a balloon and fitted with a wire mechanism. The biggest plant-eating dinosaur that ever roamed this planet. It moves about almost lifelike. Nabbits are controlled by microcomputers and can move swiftly and smoothly without any of the cold mechanical actions characteristic of robots up to now. This little one is drawn into the world of fantasy by this gigantic laughing tree. This 5-meter-tall gulliver tries to capture passers-by. The elephant blows his trumpet as he moves about almost lifelike. Starfish, sea urchins, coral, the 20 or so babbits on display were an introduction to the infinite possibilities opened by this new field of formative art.
Oh yeah, this is about 40 years ago. Okay, more than 40 years ago. And RALPH, yes, the Stanford University RALPH is here. Some hand gesture can be produced. Yes, like this. And also, yes, Hitachi's line. Presently, it's very, very commonly used. Some animation system or learning system or something. Yes. Yes, the second part of this talk, today's talk, is a visual sense. Visual sense. In the human eye, we have some cornea, and crystal lens, and the glass body, or this is a ciliary muscle to change its with the thickness of this lens, for example. Yes. There's some retina is here. Retina structure looks like this. This is inside of the glass, and some layers. It has some layers of the nerve cells. Nerve cells are arranged in some layers, so it makes some network. So that is a retina pigment cell is here, and extraocular cell and the entoretina. There are three kinds of cells: the photoreceptor cell, horizontal cell, bipolar cell, and also inside the amacrine cell and the nerve cell is here. So I will show some video.
Light rays enter the eye through the cornea, pupil, and lens. These light rays pass through the vitreous, a clear gel-like substance that fills the middle of the eye. The light rays are focused on the retina, a light-sensitive tissue lining the back of the eye. The macula is a very small area at the center of the retina that gives us our fine pinpoint central vision. The area of retina surrounding the macula gives us our peripheral or side vision.
Yes, it says this part makes the most precise discrimination of the vision, because the nerve cells, the retina cells, is concentrate around this area, and for surroundings, it become layer. So yes, maybe you can find your visual sense is also the center of the visual sense is the most precisely, and around here is become more lower density, maybe, so you can understand. And also around this spot is some nerve strings is yes, it is a nerve string is to go through the brain, so that this part no visual signals, visual cells, so this part we cannot see this part, okay, we cannot see this part because no detector. This nerve cell is around here. It is go to the brain. So around this part we cannot see. So maybe you can see all this, but only some part we cannot see. Okay. Yes, it is explained.
The retina converts the light rays into signals that are sent through the optic nerve to the brain.
これはないですね。どっかに多分ね。Yes, maybe you can. どっかちょっとこれを見てみますか。Yes.
The human eye is a complex organ that provides visual sensory information to the brain. Each part of the eye performs a specific function. The retina is responsible for receiving light information. Its pigmented layer helps to capture light. The retina's sensory layer has rod and cone photoreceptors that detect and translate light information into nerve impulses. The signal is passed through the retina's layers of neurons and carried to the optic nerve located at the back of the eye, where the signal is gathered and sent to the brain. Degenerative diseases of the eye, such as retinitis pigmentosa, affect the photoreceptors and cause damage to this pathway of information in the retina, leading to irreversible vision loss. Most adult organs, like the eye, are not capable of repairing their damaged or diseased cells. However, stem cells have the potential to replace damaged cells with healthy ones. This is because stem cells can generate new cells of the same tissue type in which they are found. Current research in transplanting photoreceptors derived from adult stem cells may provide hope for patients afflicted by these diseases. Certain parts of the adult body maintain a population of dormant stem cells. One of these populations can be found in the retina of the eye. These retinal stem cells are located within the dark ring around the iris and the pigmented epithelium near the ciliary margin. Of these cells, about 1 in 500
This is a
are
little
actual
bit
stem cells.
complicated in detail thing. So we can skip here, and also this, yeah, to skip here. So to move to the some support system, substitution system, or auxiliary system, one of the things you are familiar with is yes, Braille. Braille is a 6-dot developed by the French person Louis Braille, developed about 200 years ago. Yes, by him. The one character, alphabet one character is expressed by this 6-dot. 3 by 2, 6-dot. Learn Braille in one lesson. Yeah, yes, skip here. So and also the important point is remarks is yes, who is blind person is the congenitally blind or accidentally visual disabled. This is a very important point because those who cannot see from his birth, they are from this birth. So it is very hard to learn about characters or outer world or something. But the accidental visual disabled is he can learn in some part about something. Okay, for this is depending on the development of a brain. Yes, human brain is developed by learning is very important. Learning is very important, and the visual signal is also important to stimulate the brain. As I told last week, the visual information is more than 80% for the human being's information. So the visual stimulus makes the very large amount of part of brain development. So the accidental disabled is it's a little bit good condition. But the blind from his birth is very severe because no learning on the brain about the outer world or other things. So you have to think carefully about the since birth blind or the accidental blind. Okay? Pattern recognition ability based on the visual experience acquired by learning. Yes, the neural network self-organization is promoted by visual signals. Okay. Yes, and in other part is next part is I have shown in the video the octagon is visual information is translated into the mechanical vibration. So the fingertip can detect the characters. Yes. For example, the index finger is put on here. So put on here on the left hand, and right hand the grip this small camera, and trace on the characters, letters, strings. And watching this camera, in the black and white can be represented in the vibration of these pins, mechanical pins. Okay? Yes, I have shown this video, and maybe you can watch afterward other videos if you are interested in. And also the similar system is also developed more than 40 years ago, about 50 years ago. using the TV camera or some the glass eye. The stimulation method is mechanical stimulation or the electrical stimulation on the stomach or the back. Yes. Yes, looks like this. Sometimes it's a mechanical pin, and sometimes using the electrode is used. Yes, I will show this video. Yes, if you want to talk more, you should go out from the room. Okay? You understand? You understand? Okay.
A forehead retina system. In our information-intensive society, the amount of visual information is increasing rapidly, and the visually impaired are facing ever greater obstacles in their everyday lives. There have been numerous proposals to restore the sense of sight by surgical means. Direct stimulation to the visual cortex by an electrode matrix is a well-known example. However, these technologies are not yet mature and may require at least a decade to be put to practical use. On the other hand, there have also been many works on sensory substitution, in which visual information is converted to tactile or oral information. However, none have become widely used for two reasons. One is the technicalities of stimulation. For tactile devices using a large number of mechanical actuators, the system becomes heavy, expensive, and requires a considerable amount of power. The other reason concerns the region of stimulation. Many previous proposals put vibration motors on the waistcoat to stimulate the skin on the back. It is surely wearable, but it is not as facile as most successful carry-on devices such as eyeglasses or cell phones. At SIGGRAPH 2003, we presented Smart Touch, which was a visual to tactile conversion system for skin on the finger using electrical stimulation. The user touches a thin plate which has a 4x4 matrix of electrodes on one side and the same number of optical sensors on the other side. The device allows people to feel surface visual information by tactile modality. We now proceed to the next stage by proposing what we call a forehead retina system, or FRS. A small camera mounted on a pair of sunglasses captures the view in front. Outline edges are extracted and converted to tactile sensation by electrical stimulation. 512 electrodes, or 32x16, are arranged at a 3mm interval and driven sequentially to present rich 2D information. Compared to previous vision substitution systems, the electrical stimulation method is lightweight, cheap, scalable, and consumes much less energy. At the same time, since the forehead is used as a stimulation point, it is much easier to put on and to take off, while coordinate system transformation taking place in our brain is much more developed for our heads than for other parts of the body.
Yes, this is looks like a headband type stimulation device, and watching by this camera, and this visual information is the outline of the visual information is represented as the vibration signal of the head-mounted this device. Okay.
FRS enables visually impaired persons to effectively see objects without touching them directly.
Yes. The next part is this is also tactile vision, is also the similar system. And the next is a walking aid for the blind patient. Walking aid. Some white cane or yes, DTBSS is or Optacon is used. And yes, looks like this white cane or something. I will show. Yes, this is a MOAT sensor. MOAT sensor is an ultrasonic sensor to detect the obstacle to walk. So the projection part and the signal receiving part is here. So by using an ultrasonic sound signal, the distance can be measured, and also size and the distance is depending on the size and the distance of the obstacle, the vibration will be generated. So this is the first type is a motor sensor. It is called motor sensor, and New Zealand made. It's about $800. But recently, the more smaller devices is developed, has been launched about 80,000 yen, only 40 grams. It looks like this. これちょっと見ますか？ミニカインド。Yes.
Today we are demonstrating the MiniGuide US remote unit distributed by the American Printing House for the Blind. The MiniGuide US is a handheld electronic travel device that is intended to be used with a blind person's primary travel method, such as a human guide, cane, or dog guide. The MiniGuide uses ultrasound to detect objects and gives you physical or auditory feedback by vibrating or chirping more rapidly as you approach an object. The MiniGuide has 5 ranges it can be set to, depending on personal preference or situation.
Yes. Yes, this is a glass, ultrasonic wave glass. Sonic glass is a product's name. So this is the ultrasonic projector and also the receiver using the earphone, both ear. So the obstacle position is also informed by the auditory information for both ears. Yes, I will show this glass.
RNIP, supporting blind and partially sighted people.
Hello. If you're a long cane user like I am, you're going to know what it's like when you bang your head on an overhead branch or post or something that's at head height and gets in your way. Or bleed 3 times, and that tells me that the
おじさんの話は後で you have some time you should hear. And also the cane, laser cane is yes, also the ultrasonic sensor, ultrasonic sound is produced from the cane. This is the top of the cane. So if it is also detected some obstacle or something. Yes. For example, this device, it is projected 3 different directions. So one is for the forward, and one is for the ground, one is for the more higher positions obstacle. Yes, three positions. Some ultrasonic signal is produced because in this case of these steps, it can detect by this lower ground signal, and also this is a higher seeding of obstacle or something. It can detect by this direction sound signals. Okay, so the 3 different direction signal is necessary for working. K-BAT sensor. K-BAT sensor is almost the same product.
Hitting a ball may seem like a simple everyday action, something most of us take for granted. But what if, like this boy, you were completely blind? How is this possible? And what about riding a bicycle when you haven't been able to see for 25 years?
It's a challenge to the mind to experience certain things or to achieve certain things that seem unachievable.
47 years ago, Professor Leslie Kay read a newspaper article about a blind school building a swimming pool.
The blind boys in a swimming pool will bump each other and not know where the sides of the pool are. This was my rather naive idea. But from there, it developed into me thinking of something to help them walk about instead of swim.
Anti-submarine detector. ASDIC for short.
Leslie knew about sonar. His story reads like a classic war movie.
おお、レズリー・リュウっていう人ですけど、yes, he is a guy of the Leslie Liu, so he is yes, developed this product now, and he is inspired by the sonar sensor in the submarine. So it is yes, firstly tried by the laser cane, and the next presently is a bat case sensor K sonar is his product. Yes, and also in Japan, some guide dog is also developed. This is the project only more than 30 years ago. So it is a large, big size and heavy product. But yes, if we develop the present using present technology, it will become more smaller and lightweight maybe. But in this case, this is not good for the patient, and also the sound nerve belt is informed about the obstacle condition or something. This is a ultrasonic sensor array, as you can see here. And by using the ultrasonic sensor, this is a walking guide cane. This is no producing some moving direction, not the mobile robot. It can only change its direction by detecting the obstacle. This device only change its moving direction. So the patient can only follow it moving to avoid this kind of obstacle. ちょっとこれは見ましょうか。The guide cane. Michigan ですね。University of Michigan.
Research scientist Johann Borenstein and his students at the Mobile Robotics Lab have many years' experience in developing obstacle avoidance systems for mobile robots. Using ultrasonic sensors, these systems can steer heavy mobile robots safely and quickly around unexpected obstacles.
ウルトラソニックセンサー、here.
In earlier work, Dr. Borenstein was able to apply his obstacle avoidance methods to powered wheelchairs, and with limited success, to a portable navigation aid for the blind called nav belt. The nav belt was designed to generate stereophonic sound signals that could guide the user around obstacles. But it was found that users could not react in time to nav belt signals, especially when they walked quickly. Listening to these signals also required a lot of concentration and was considered tedious. To overcome this problem, Borenstein invented the guide cane. The guide cane has ultrasonic sensors and a steering mechanism just like a mobile robot. However, the guide cane can be made lightweight and portable because whereas the steering mechanism is powered, the wheels are not.
Only steering
In
mechanism.
operation, the guide cane is pushed along in front of the user. When the device detects an obstacle, it steers around it. The user feels the changing orientation of the handle and can follow the avoidance maneuver immediately and without a conscious effort. In just 1 year, Dr. Borenstein and graduate research assistant Ivan Ulrich built the first working prototype of the guide cane. This prototype included 8 ultrasonic sensors, an onboard miniature computer, and a small servo motor for steering control. Here, Ivan demonstrates the capabilities of the early guide cane prototype. Blindfolded, he has to rely completely on the guide cane as he walks through a cluttered obstacle course. The same month, from a different perspective demonstrates the steering activities of the guide cam. Also, there is the rapid clicking sounds caused by the firing of the ultrasonic sensors. While Bornstein says there is still a lot of room for improvement, he believes that a commercial version can be available in 2 to 3 years.
It says commercially version will be available 2 or 3 years とか言ってるけど、but it's not commercialized because because only the limited floor space can be used and some steps or it cannot deal with some steps or some road uneven conditions, so it is a little bit difficult to use. And also this is only for this device chip, but for the patient. So it's a little bit distance from this device and this patient. So this device can completely successfully avoid the obstacle, but sometimes the patient can hit the obstacle. So it is not so. In some cases, it is not so good solution. Yes, and moreover, recently, some bionic eye is inserted. This visual signal is the electrode is directly attached to the brain nerve. And also, this is a voice. Yes, I will show this video. Bionic eye ですね。
Sight was once the stuff of science fiction, but now it's becoming a reality. Scientists in America have developed a bionic eye implant which could help restore some vision to millions of blind people. Our science correspondent, Christine McGurty, reports now from California.
No one expects Grandma to play like a professional, but for Linda Morford, that any ball goes in is amazing. She's totally blind. The small circle in her glasses is a camera. Some clever electronics turns the images into patterns of dark and light. It may not sound like much, but for Linda, it's made a huge difference.
Instead of having to listen for what's around me or who's around me, or to feel what's around me or who's around me, I can actually see them again.
So how does her eye implant work? It's designed for people who are blind because light-receiving cells in the retina are damaged. An implant is attached to the retina to bypass the damaged cells. Images from the camera are sent to a processing unit and onto a receiver behind the ear. They are then transmitted along a wire under the skin to electrodes on the implant. That sends pulses along the optic nerve to the brain, where they are turned into patterns of light.
This is it. The implant is a little sliver of plastic with electrodes embedded inside. It's light and flexible and feels a bit like an ordinary contact lens, but it's a tiny piece of magic with the ability to transform some people's lives.
When the first operation was carried out, no one knew just how the eye would respond. But now a new trial is set to begin, with 50 to 100 patients and a new improved implant.
I have a vertical point bar placed on the wall. What I'd like you to do is scan your head back and forth and just point to the object when you find it.
Linda's sight is rudimentary. Scientists can't be sure exactly what she's seeing. Here, the computer gives some idea. Each circle represents one of the 16 electrodes on the implant. With 60 electrodes, the new implant should provide much better definition like this.
We hope that'll provide orientation type vision, allow these subjects to not bump into tables, be able to know where the doors are, where the window is, be able to even recognize the overall form of a person.
Daily life for Linda has improved. The hope is that one day others like her might recognize faces, perhaps even read. Christine McGurty, BBC News in California.
Yes, this is a case. This video's case is in the retina. Inside the retina, the electrode is directly attached to the retina's part. Okay. ちょっともう時間がないので、yes, maybe if you are interested in, you should see this this voice, yes. And yes, that's also almost finished. And the final information is this: is industry academic cooperation fair will be held this tomorrow and the day after tomorrow. And in here, this science and research park. For example, the exhibition will be held at the gymnasium. It will be exhibited some robots, such kind of leading robot by Professor Kamata, and autonomous vehicles by Professor Ogai, and others. Kyushu Institute of Technology's laboratories, many kinds of robots will be presented, will be shown here. And Yasukawa Electric Corporation's industrial robots will also presented. Maybe I don't know exactly which robot will be exhibited, but you can see this. And also the keynote lecture will be held as the opening ceremony. It will be held tomorrow 2 p.m. and 1 hour presentation by President COO by Yasukawa Electric Corporation, Mr. Tsuda. Will present there, but it is so limited in Japanese, but you may understand by some figures and movies maybe. So if you are interested, you should attend there. Okay? And the seminar, also several seminars will be held. For example, the Friday morning, the recent topics about robot technology, and also the Friday afternoon, the upper limb rehabilitation robot, training robot will be presented by the former Sangyo Ika Daigaku's doctor. Yes. So if you are interested, you should, yes, it is free of charge, so you can attend. And also the most important information for you is you should, if you bring some report addition to the usual subject, I will add some scores, points for you, okay?